Okay, good morning and a happy Thursday. Obviously, I'm unable to make it today. I physically can't make the 45-minute drive down there today. I plan on coming in on Friday. Um, so again, hang in there. We'll make do and get some reviewing. One thing we need to do for uh, periods 1, 2, and 7, 8 is make sure that we know our final. Let's just do that on Tuesday. That'll leave Monday open during our time slot for, I guess that would be first period. We can, as well as 7th period, and we can use those for review if you can make it in. We'll take advantage of our double periods. For the 3-4 class, we'll do the same thing. We already know our finals on Wednesday, but that 4th period slot on Monday we can use for review if you want to come in. Okay, so today let's keep the focus on energy. Yesterday, hopefully, you were able to review Newton's laws and motion in general. In the book, energy and work are done in 6 and 7. Okay, so the big idea is, of course, kinetic energy is always going to be there if you have motion. It's always a positive number. Potential energy, on the other hand, is a little bit trickier to work with. It's energy due to position. That is, you can define a reference point. For example, if you're using MGH, keep in mind that old idea of you have to define where your height equals 0 is. So different people can have different measures of potential energy if they're using different reference points. That's fine. So for individual energies, yeah, you can have, it's pretty arbitrary. However, what we do have to agree with, even if we're using different reference points, is when you have changes in energy. That's actually turns out to be more important. So the 3 main types that we use for like everyday situations, just lifting things, roller coasters, whatever, is MGH. That's an approximation though, because when you talk big distances, gravity changes. So technically, to do gravity right, we've got this funny negative energy, negative gmm over r. That came when we did an integral, okay, an antiderivative of our gravitational force. There is a video on the blog for that. I won't go into details here. We have elastic energies for springs, primarily. 1/2 kx squared, x is your displacement. How far you either compress or stretch a spring. There's also a video on springs, if you want to take a look at that for review. Again, I'll keep reminding you that there's all sorts of worked examples in the book, which would be very useful. We have those so-called potential wells, where the main expression, we're relating forces with potential energies. This works, this negative derivative idea works for all the forces we do, with the notable exception of friction forces. Okay. So in other words, things like gravity, electricity, springs, really what matters there is just the changes in position. Okay, the path doesn't matter. For friction though, since friction's on all the time, the path does matter, and this relationship doesn't hold true. So there, for potential wells, again, there's a how-to video on the blog for that one. So I'm not going to go into detail here. Okay, major rule, conservation of energy, of course. This is a incredibly useful thing, but just in the practical sense. You can solve all sorts of problems with this. And in general, keep in mind we use energy if we're looking for speeds. It's definitely going to be easier than doing Newton's laws. It's also much easier to use energy if you have non-constant forces. That way you tend to stay away from calculus and the heavy-duty math, again, especially if you have to find speeds. Conservation, don't forget, applies to the whole system. Okay, for an isolated system where energy doesn't come in or leave, the total energy has to stay the same for all the pieces of that system. Now, individual objects interact and their energies change all the time, but that's a transfer of energy, so that the total for the system stays the same. Okay. Technically, now since we did a little bit with relativity, and don't worry about it, relativity on the final. E equals mc squared tells us that, in particular for nuclear reactions, conservation of energy by itself, conservation of mass by itself, don't work. So we technically have what we call the conservation of mass energy. And they turn into each other. Okay, so in terms of solving problems, this is the kind of the starting point if you're using energy. Your total initial energy is equal to your total final energy. And on the final side, don't forget, if we have friction, we have to account for the heat. Okay, that's the work that friction does. So that'll just be the friction force times the distance that the friction acts on the object. Okay. Now, since we just mentioned work, work is a transfer of energy. That's when forces are moving things. It can either, a force could be applied in the direction of motion, it can be applied opposite the motion and slow you down, for example. So you're most used to using the dot product form. Okay. Force times the distance you go times the cosine of the angle between the two. This here we jazzed it up just a tad. We say it's the integral of force times displacement. And this way, this version, which is on your cheat sheet, allows us to work with any kind of force, including non-constant forces, which in the past you may have been restricted from doing. Now, because it's an integral, if we've had these graphs before where a force position graph where the area below that graph is the work. Okay. So graphically, that's what integrals do. Or we also have a second way of thinking about work, and that's when your energies are changing. That's the transfer of energy that we talk about. If a force makes you go higher and higher, then that work is doing, or that force is doing work on you because it's increasing your potential energy. If you kick something, where it goes from rest and then it has some speed, okay, you just increased the kinetic energy. That doesn't happen by itself. You had to transfer energy from your body to the object. Keep in mind, work can be positive or negative. It's positive if the force and the motion are in the same direction, or if they have components in the same direction. And typically that means that you're speeding up, or you're going higher, or you're stretching a spring, or something like that. Work can also be negative, don't forget. And that's if your force and your motion are opposite each other. So the classic picture is something like this. You're dragging something or pushing something along a surface. In this case, a component of your force and the motion to the right are in the same direction. That would be positive work, because the cosine of that angle would be a positive number. Whereas in the case of a friction force, friction is going opposite the motion, opposite your displacement, and so there you'd have a cosine of 180 degrees, which is going to be negative. So friction is doing negative work on the object. It's trying to slow it down, taking energy away in the form of heat. Okay. The last thing, which is kind of a secondary topic, it's not so important, but we did just a tad with it, is when you measure your horsepower. Okay, so technically power is the rate at which you do work. The rate at which you create energy, the rate at which you use up energy. So that has time in it. So for example, when you ran the stairs, the work you did, you increased your potential energy and then it took a certain amount of time to do that, and that gives you watts of power. Keep in mind, just generically, there's one other expression that you can use. Since you have work on top, work is force times the distance. If you think of that ratio, distance over time, well, that's velocity. So I think this might be on the cheat sheet, I forget. So another way of finding power is a force multiplied by velocity. And technically that too is a dot product, since those are both vectors, and power is a scalar. Okay, so anyhow, these were the big ideas for energy. The substitute should have an energy review set. The 3-4 classes get an additional set that'll have some rotations and stuff on there. Speaking of rotations, this applies for the 3-4 class. The other two classes can ignore this. Keep in mind, the big thing with rotations is you have rotational energy. 1/2 I omega squared. So we do energy exactly the same way that you've always done it, but you have to consider anything that happens to be spinning when you do conservation. Okay, well, again, make real good use of this time that you have. Work together, help each other out. Look at old tests and homework problems, AP problems. You have all those different resources that we mentioned yesterday. If you want to see any of these videos during class, the substitute will allow you to, and maybe you and some partners can get onto one of the computers and watch them, and try the review stuff. And I should see you on Friday. Take it easy. Bye.